Welcome to part 2 of our session on corrosion protection. What you've observed in the photos that Jeff shared is that there is a wide range of corrosion performance possible with a single corrosion protection system. So we're going to transition to focusing on some best detailing practices for achieving optimal corrosion protection. And we'll also review the current state of practice regarding estimating service life of those corrosion protection systems. Before getting started on the technical details, I'd like to take a couple minutes to put this seminar into context for you, starting with the big picture of how I got started thinking about corrosion protection. So as Jeff mentioned, a lot of us think of design and design of very grand structures like the one shown here, which some of you may recognize as being the New River Gorge Bridge in West Virginia. And this bridge was one of the first long span bridges in the United States that was built from uncoated weathering steel. So it was a feat of engineering when it was built in the 1970s. But the concern for this bridge and most bridges going forward is its long-term performance with respect to corrosion. So my experience with corrosion topics began about 20 years ago when working on a project where I inspected about 100 uncoated weathering steel bridges, including this bridge, and having the exciting opportunity of crawling through the interior of the boxes forming the arch. And since that time, the performance of uncoated weathering steel has been one of my primary research interests. So as we move forward, you'll see that the majority of the photos shown are of uncoated weathering steel. However, the detailing principles that we discuss are generally applicable to all corrosion protection systems. So moving into our discussion about detailing, our main goal is to review some of the more subtle features of a structural design that affect its corrosion performance. The main factor affecting this performance is water. On campus, my office is in the same hallway as some environmental engineering faculty, and there's an eye-catching poster there with the tagline, "Water is life." While this is certainly true if you've already gotten a morning run in or have done something less or more energetic with your day so far, or in order to provide the lush vegetation on my favorite mountain biking trail, water is not a friend to steel. You can see evidence of this in the painted steel structure with an open grid deck, which is creating the shadow pattern that we see on the photo in the top right, and the associated failing paint and corrosion at the connection between this floor beam and stringer. The open grid deck allows for regular exposure to water. Similarly, we can see in the photo in the bottom right that the bottom flange of this beam is exfoliating sheets of rust while it sits on a concrete substructure that is obviously retaining water based on the darker color concrete on the left and top edge of this concrete member. So water is essential for life, but we should make a concerted effort to keep it away from our structural members. I'm going to do a quick review of chemistry to provide the why for this point, for why is water bad for steel. So first, recalling the main element in steel is iron, Fe. Then digging a little deeper into our chemistry backgrounds, you may recall that iron has a natural oxidation state of +2 or +3. Meaning that when exposed to moisture, 2 in this example, or 3 electrons are readily lost in solution. So if you'll bear with the chemistry here for just a minute, in the atmosphere of Earth, where oxygen and water are abundant, these electrons result in the formation of hydroxide, OH, ions. Those negatively charged hydroxide ions easily react with the positively charged iron ions to form iron hydroxide. Then when the moisture evaporates, dehydration causes a rearrangement of the atoms into what is widely known as rust. Here we are looking at one of the simpler of a few possible ways of getting rust, but what all of these reactions have in common is that rust cannot form without water. It's a necessary compound to set off the chain reaction by causing the dissolution of iron into the positively charged iron ions in the first step. And the chain reaction cannot proceed without water to produce the hydroxide ions. I'll also make mention of chlorides as we review detailing practices. Chlorides and other salts regularly come into contact with bridges due to their use as de-icing agents for winter roadway maintenance and the presence of airborne chlorides in coastal locations. Similarly, review the chemistry for why this is problematic. We saw in the first step of our chain reaction for forming rust that the formation of rust is an electrochemical reaction, with the electrons traveling through films of moisture on the surface of the steel, and chlorides form dissolved electrolytes in the solution, which means they act as a catalyst, increasing the rate at which rust forms. So hopefully now that I've convinced you that you should minimize water on your structural members, let's think about where the water will flow in different conceptual situations. Considering that our structures are going to be exposed to water from rain, for example, we can think about structural details as falling into one of three categories. The best scenario is when we have water on a member, it easily flows off the member unobstructed. And we call this situation free draining. Other situations that can occur are that the water becomes trapped or ponded. So the main concept of detailing is to always ask ourselves if the water will be trapped or ponded by any particular detail that will create the prolonged presence of water and therefore create rust. Note that this is exterior rust in steel members, easily visible, and this is interior rust on the rebar in reinforced concrete members. So I'm going to review 4 examples of details that trap moisture and 2 examples of surfaces susceptible to ponding. Note that the details that trap moisture also typically trap debris, which then retains even more moisture, creating an exponential effect for that situation. So starting with a routine girder bridge, locations for trapped debris and trapped water occur where we have reentrant corners, or in other words, where intersecting plates form 90-degree angles with one another. One example of this is so-called drip bars, which are sometimes used for aesthetic reasons, which we will discuss later, on uncoated weathering steel structures. You can see in the top photo the accumulated debris piling up in the corner between that drip bar and the web and the flange, and the trapped moisture that likely occurs in that situation. The remedy to this potential problem is shown in the bottom right, which is a standard detail recommended by NSBA, where the basic principle is to orient the drip bar at a 60-degree angle from the web. Vertical stiffeners and cross-frame connection plates create similar opportunities for trapped water and debris, and for that reason, it is recommended to minimize the number of such plates to the extent possible, and consider providing corner clips that allow for drainage around those plates where they are required. Other considerations for cross frames are their orientation. What is shown here is the projecting eccentric leg of the angle cross sections commonly used in cross frame members oriented on the top surfaces of those members. This provides a degree of shelter for the rest of the member and reduces the potential for water and debris accumulation on the cross frames. Another recommendation shown in this illustration is providing a tight fitting filler plate to eliminate a gap between the cross frame members, which is another susceptible location for debris accumulation. With those exceptions, girder bridges are relatively straightforward to detail. More complex structural forms need additional considerations regarding corrosion. One of those is the point of termination of inclined members. These need to be considered to avoid providing a trapped drainage situation. So we're showing 2 examples of that here, an arch on the left and a steel frame on the right, where drainage was not provided at the ends of the long inclined members of those structures. In both cases, the ends of these members became locations where significant water and debris accumulated. This is evidenced by the muddy appearance on the close-up on the left, where visible changes in the thickness of the steel plates on the left side of the photo can be seen. And we also see localized corrosion clearly evident in the close-up on the right. In both of those locations, drainage holes are needed and regular maintenance of those details are needed, such as during the biannual inspection of those bridges, to ensure that there's drainage provided and that it's unobstructed and working as intended. Another more complicated situation is the bolted connections in closed shapes and the hand holes that are necessary to tighten the nuts on the inside of those box members. This is another location where water and debris can easily accumulate, as shown for the truss structure in this example. In the center photograph, you'll see several of the bolt heads are marked with yellow X's, each of those representing a location where the bolt is in need of replacement due to excessive section loss. And that section loss is shown in the photo on the right by the irregular shape of the bolt shanks shown there. In this situation, similar situations like this, the recommendation would be that the handholds should be sealed with a semi-permanent solution, one that is watertight, but also can be removed to allow for future inspection. Moving into some of the situations where ponding can occur, we can think of the deck of bridges as forming a roof for the steel members comprising our superstructures. The better our roof, the better our corrosion performance will be. Shown here are a couple examples of our roof being smaller than ideal, meaning that the bridge deck overhang is narrow relative to the depth of the girder. The consequence of this is that it allows rainwater to accumulate and pond on the exterior surfaces of the bottom flanges, creating rust in that location. Furthermore, capillary action, which we see anytime we throw a paper towel in a spill and see the water quickly seep through the portion of the paper towel not in direct contact with the spilled beverage. This action pulls the water up the surface of the web, resulting in the darker colors at the bottom of the web, which is also an indication of rust at the bottom portion of those girder webs. In contrast, a wider overhang, either one approximately equal to the girder height where this is possible, or as wide as practical otherwise, provides more shelter to the exterior girders and prevents ponding and the associated capillary action on those surfaces. A worse but less common example of a bad roof is the use of discontinuous deck materials like timber or filled or unfilled metal grid decks. So these types of decks should be avoided, or the structures where they are used should be designed expecting corrosion and or the need for maintenance on a shorter time frame than other structures. In the case of timber decks, these can cause a nearly continuous moist environment, and a similar situation eventually happens with filled grid decks, which crack over time. In the top left photo, you can see darker colors on some of the wood planks, indicating that they are wet, despite the absence of rain in several days when this photo was taken. And a close-up of this bridge on the bottom left shows the layer of rust on the top of the top flange that occurs in that situation. Top right photo shows a similar situation where the paint is clearly bubbling away from the steel and the resulting formation of rust in that situation. And the bottom right photo is showing an example here from a lovely day with Pedro Albrecht, and watching him easily pry loose with his hands what used to be the bottom layer of the steel grid deck. So we've established that a free draining structural detail is the ideal scenario, but one free draining situation that needs great attention to be avoided is a leaking joint. While we want free draining situations, we want them where we've intended, and a leaking joint is not typically designed for. Furthermore, it provides a concentrated amount of water in one location And even worse, that water is often laden with chlorides, at least in the northern half of the country and a large portion of the year. So the photos here show some of the effects of this for both steel and concrete members. To give some context for the scope of this problem, the findings from a review of 70 inspection reports in 4 different agencies found that approximately 1/3 of the bridges reviewed had worse performance below the deck joints than in the remainder of the structure, indicating leaky joints and poor performance associated with those leaking joints. 2 of those agencies were in places where de-icing salts are used regularly, and 2 were in locations where the bridges were in relatively close proximity to the coast. One thing we can see from this data is the possible effect of maintenance practices, in that only 3 out of the 4 agencies were having this problem. So given that leaking joints are a frequent reason for compromised corrosion performance, the joint design should be a key consideration for the designer. One partial solution to this problem is that for uncoated steel, painting below all joints is a standard recommendation that should always be prescribed. It should be assumed that the joints will leak at some point in the future, and even the agencies with the most aggressive maintenance plans do not have the funding to immediately detect and also replace every leaking joint. And this is a situation where a small amount of paint can easily offset much more significant corrosion problems in the future. A better solution is to eliminate the joints as much as possible. One way to do this is with integral or semi-integral abutments, where the beam is cast into the concrete back wall and thermal movements are accommodated by the back wall. This obviously creates rotational fixity at the end of the beam, which can also provide the benefit of reducing the maximum major axis bending moment needed to be resisted. However, for curved and skewed bridges, fixity about the minor axis of the beam can be a concern. Thus, integral abutment bridges are not regularly used in highly skewed or curved bridges. In these situations, one option is the so-called Virginia abutment developed by Virginia DOT staff. And in this case, the girder is cast into a concrete diaphragm, and then the bridge joint is placed behind this diaphragm and drains into a concrete trough behind the superstructure. This provides the same corrosion advantages of the integral or semi-integral abutment bridge, but with a simpler substructure design. A third option for eliminating joints, in this case joints along the length of the bridge, is to use so-called link slabs. These are often used in multi-span systems that are designed as simply supported for dead load during the initial construction, but then a concrete closure pour, shown in the shaded gray portions of the figure, closes that joint that previously existed between the spans. A similar concept can be used at the ends of the bridge by extending the concrete deck past the end of the abutment back wall, which again has the same effect of moving the joint off the bridge. A couple other considerations for drainage include that when there are other components of the drainage system, they also need to be designed and maintained so that the components themselves do not cease to be functional due to corrosion. Here we are seeing the bottom portion of a drainage pipe with the center of the light indicating the present top end of this pipe now that the original top portion is broken and is now no longer attached to the rest of the drainage system. Similarly, because it can be expected that the drainage systems will become clogged or perhaps corroded themselves and thus have reduced functionality, it's recommended to minimize the use of scuppers. If scuppers are believed to be necessary, then having a fewer number increases the flow through any single scupper and provides a higher velocity flow that will reduce the likelihood for the scuppers to become clogged. Lastly, let's review 3 design considerations with respect to corrosion that are not directly related to detailing for water. For uncoated weathering steel, there are existing guidelines from the Federal Highway Administration on avoiding the use of this material in 3 general environments: marine coastal areas, areas with high rainfall, humidity, or fog, and industrial areas in close proximity to chemical fumes. And 2 more specific locations: grade separations and tunnel-like conditions, which is defined as a highway overpass with relatively small vertical or lateral clearances, and low water crossings with the dimensions that you see listed there on the slide. So these should be considered as a starting point for whether or not to go with, as Jeff described it, the default material choice of uncoated weathering steel. What we'll see here, though, is that those requirements are largely qualitative at the present time, and FHWA has ongoing research aimed at removing some of the subjectivity in these guidelines. And this should be forthcoming within the next year, so that research will answer questions like how far from the coast defines a marine coastal environment, how much humidity is too much, how high of a vertical clearance is needed for a tunnel-like condition, how much salt use is needed in that situation, etc. There's sometimes aesthetic concerns of the initial oxidation of uncoated steel causing rust staining on concrete substructures, and there are various schemes to help reduce this staining. One of them is wrapping the girders with plastic, which is shown in the photo here, and then applying a sealer to the substructure. And this bottom photo shows the effectiveness of this practice on a 20-year-old bridge where a substructure was initially wrapped and sealed, and then after 20 years, the concrete looks essentially freshly cured. Another strategy for preventing substructure staining is the use of drip bars to divert the water traveling along bottom flanges before it reaches the substructure. These are easily fabricated, and the AASHTO NSBA collaboration document on guidelines for design details gives a standard detail for this. One caution here, though, with drip bars is that welding these to the bottom flange can create a category E prime fatigue detail. These are not typically used where there are high stress ranges, but they should be checked for fatigue. And there are alternative drip bar configurations that avoid welding detention flanges if needed. Last note on detailing is considering vegetation. Here we see the effects of vegetation growing on and in close proximity to a structure, and the resulting section loss of the scupper, shown here, and 100% thickness loss, section loss of the web adjacent to a vertical stiffener. The vegetation is creating a localized peak in humidity and more opportunities for water to condense on the steel, as well as the possibility for trapping debris on the structures. So I'll wrap up with a few comments on service life of the various corrosion protection systems for steel bridges. And start with the point that hundreds of thousands of steel bridges in the US show that steel bridges perform well and can easily provide a long service life, especially when they are detailed properly, as we've been discussing for the past 25 minutes. How long, though, is not an easy question to quantitatively answer as of today. And reasons for this are that the long-term field data in realistic and representative environments is sparse, and that numerous variables affect performance. These include the environment and the numerous environmental parameters that are influential, such as humidity and snowfall and rainfall and proximity to the coast, etc., as well as maintenance practices and workmanship. With the photo here showing a suspected case of poor workmanship due to the abrupt changes in the performance of the paint along the length of this girder. More information on service lives, though, is anticipated to be forthcoming through an NSBA AISC funded project that I'm leading, where we are aiming to provide estimated service lives of 6 of the more common corrosion protection systems in 2 representative environments, which can then be used as a basis to calculate life cycle cost for each corrosion protection system. So I'll quickly conclude with some acknowledgements, with thanks to Jeff for sharing some of his excellent graphics, and to the funding sponsors who have provided the resources for compiling this information.